So thank you again for having me. Okay, so just to give a quick reminder what I did last time. So I introduced a type theory with a heterogeneous equality. And this heterogeneous equality lives in a different context, which I call gamma equal, in the context of triples, basically. And it relates different projections of the same type into this extended context. And this came together with this context morphism from gamma equal to gamma. Since I said gamma equals is tripled, so in particular we have the zero projection, which projects out all the zero component, and the one projection. So that was the first step. And then another construction is if I have a term A of A, I want that A preserves equality. And since we are in a dependent type setting, we really have to be a bit clever how to state this. And I'm saying in gamma equal, in the context where everything is tripled, now there's a proof A tilde, which proves that A projected in the zero component is related to A projected in the first component. And I defined these, so I find this by induction over A, over the type. So I did this for pi type, and I left this as an exercise for sigma types. I'm going to check the exercise in the end of the lecture. And that's that. And then we also introduced reflexivity, which, first of all, there is a context morphism, R gamma, which goes from gamma in gamma equal, sort of like the diagonal. It triples everything, and it inserts equality proofs. And the other component of this was the proof if A is in A, then there is a proof refill A that A is related to A in tilde A, and then we substitute with R. So by using R, we actually get we can recover a homogeneous equality. And maybe to remind you, I had a preliminary definition of what the equality of types is. And I said already I'm going to fix this. But let's just write it down what it was. So A is equivalent to the universe to B was just simply defined to be all relations. I maybe I should leave some space here. Okay. All relations, and the nice of way to tie the knot is now the definition of A tilde. If I have gamma A colon U, I also have to define A tilde, and just applying this formula there, A tilde has to be in A has to be a proof that A0 is related in U to A1, right? That's just unfolding this for the special case that A is actually the universe. Ah, hi.
Hello. How are you doing?
Good to see you. And big A is an element of the universe, is a type. And if I just apply this definition here, then it becomes clear that this is, that this is just the same as A0, A1 to U. And this suggests that the proof that the type A preserves this equality is just the definition of equality. Okay. So now I have a definition of equality. I have a proof that equality, so this I define by induction over types, and here by induction over terms. I prove that every term preserves equality, and we have reflexivity. We also, using reflexivity, recover homogeneous equality and a proof that this is reflexive. But we want more. We want to be able to simulate path induction. So that's one thing which is missing in the moment. We want to be able to implement, here's something. We want to be able to implement J, and although we would like to have a more sensible definition, oh, I didn't leave enough space. Oh, yeah. You would like to have a more sensible definition of the equality in the universe, because I really want this to be univalence and not this any two types which have a relation between them are equal, which is a bit much, right? That's not good. Okay. So the way I'm going to fix it is obviously inspired by this cubical set model. And let's just be very simple. Let's just add some components to this definition here. So I'm just keeping this equality, which also means that I can still, that this component here is still going to be my equivalence relation. Okay, so okay, yes. So I need some more components, but the first one is the equivalence relation. Now, what else do? I introduce a term which I call coerce, which is a function from A to B, and this is coerce in this direction. And I wonder how I survive. Okay, let's move this. This is not a very good idea. Let's move this over to here. Okay, bad planning. So A is equivalent to B is now defined as a sigma type, but we keep the first component, which is this relation corresponding to the equivalence relation. And the next one is a function from A to B, which is a coerce function, which is sort of intuitively clear. If you have two equal things, you should be able to go from one to the other. And it should be good. That means is the case that if I coerce, then I get something which is heterogeneously equal to where I started. So I need another condition, because, so first of all, I'm going to give a completely symmetric definition of equivalence. So you turn everything around. So we also need a uniqueness condition, which I'm not going to discuss in great detail, which basically says if you have an element in A and you have two pairs P prime of sigma of an element of B, which is related to A, then these two are equal. And in the current discussion, I'm not going to talk much about this component. And then I have everything in the other directions. Yeah?
What do you mean by
equal in the sigma type here. It's yeah, equal, oh, it's tilde. Okay. Okay, by equal, right, if I say A equal A, B, I mean A tilde A substituted. Okay. So then I mean I can write P equal P prime here. So this definition of equivalence of types is equivalent to the usual definition. It is actually a bit bigger because here, if you keep track of the universe indices, you see that the usual definition of equivalence, which you find in the hot book, is one universe lower than this one. But this has the beautiful property of being completely symmetric. And although it fits in because it's just an extension of this R. So that's why I use it. I don't think the size is a very serious issue because I can show that this definition is equivalent to a small one. And so it's morally small. Okay. So this condition, or this, if you look at Cui and Co, it's a particular case of a Kahn filler. Namely, it's a Kahn filler in the zero dimension. Because if I have a point here in A, and I want to fill this, turn this into a one-dimensional cube. A one-dimensional cube is a line, right? Then I add a new point, which is this Coe A, and then add a filler, which is this coherence. Okay. Now I'm also interested in Kahn fillers in higher dimensions. So for example, if I already have a line here, and I have two in this situation, let's say, no, I don't give them all names. This is 1, 0, and this is A 0, 1, A 1, 1. And here I have, what is this? A bar 0, and this is A 0 bar, A 1 bar. If I'm in this situation, I also want to have a filler, a line, and I want to be able to fill the square, and so on. So these are the Kahn fillers. Now in my setting, it seems that I can derive this one from this one, which means I don't really have to talk about higher dimension. I have to admit that this construction, I'm still a bit suspicious, so we reintroduce the higher dimensions. But what we certainly need to do is to be able to extend this translation, we have to be able to construct this structure for every type. So for every type A, I have the first component, the relation, yeah, this component here, but I also have to fill in these remaining components here, and I just write down what they are. So I need a coercion from A0. So okay, maybe I should have said that all this lives in gamma equal, okay? It lives in the extended context. So if I have a type A in U, then in gamma equal, I have a function from A0 till A1, which is what we call transport, right? If I have two types which are basically the same, then I can go from one to the other. And with respect of my heterogeneous equality, I can actually say that for any A in A0, it is the case that A is related heterogeneously to the coercion. Okay? And everything in the other direction, though, because everything is symmetric, I'm only going to look at one direction. And I have to define this by induction on A. So now, as usual, I leave the sigma types as an exercise, yeah, and just do the pi types. So the sigma types are actually easy. I mean, there's nothing exciting happen. So I'm going to do the more interesting example, the example that A is a pi type. So what do I need? So let's just write down. We know that A is a type, and we know that in the context x colon A, B is a type. Then I know that pi x A B is a type. So now I want to define coerce for this. Let me see, do I do this here? So coe, let's just write, I'm just writing pi for this type. So coe pi of an element A, F, or let's call it F, which is pi 0, and pi 0 is pi x colon A 0, and then B 0 comma x. Right, we had this before. So now I want to construct a function which has the same type but everything in one. So how do I do this? I abstract over an element x in A1. And now here I have to construct now an element of B1 comma x. Right? So how do I do this? First of all, well, it's to estimate where I end up. First of all, I'm going to use the coerce in the other direction of type A for x to get something in A0, which I can feed into my function f. And now, what I've got here is B 0 and coe so that's the variable x is defined to be, maybe I shouldn't have called this x. I call this here x1, okay? Well, so the variable x, which is a variable in B, right, becomes coe A x. And what I need here is something of type B1, where x is substituted with x1. Right? So how do I do this? I'm certainly going to apply coe B, but coe B lives in this context. So coe B lives in gamma x colon A equal. Right? So which is the same as gamma equal x0 in A0, x1 in A1, and x bar proving x0 is equal to x1. So if I want to use QEB, since in the moment, so this definition here is in gamma equal, right? Just from there. So if I want to use QEB, I have to find a substitution which explains x0, x1, and x bar, right? So how do I do this? So I do QEB up to a substitution which I call alpha, and I apply this here. And this substitution alpha works as follows. So alpha sends x0 to QE1x. It sends x1 to, okay, it's hanging on with x1. Oh no. Do I call this x1? Yeah, I call it x1. So x1 is sent to x1, which, there's some variable clashes. And now I have to prove that these two are the same, but this is the coherence of A, this is also an A, in this direction of x1. Hang on. Yeah. X bar becomes the coherence of A of x1 in this direction. Okay? So, I mean, that's, I'm sure we have seen something like this already. But in the past, when I was doing something like this, I used transport. And transport I only just get later. So here it sort of fits very nicely with these coercion function, which I've built in. But we still need to do something else. We also need to prove coherence. So we need to prove, so where do I do? Also in gamma equal, I need to prove coherence for pi in this direction applied to f. And this says f is the relation R, that's the equality which we have defined for pi to coe pi of f, which I've just defined here, right? Now, I'm sure you all remember the definition of equality for pi, right? It's just we assume two equal elements, and then the result has to be equal. So we assume, let me write this down, we assume x0 in A0 and x. So I'm going to expand this type here, x1 in A1 and x bar, which proves that x0 is the same in A as x1. And under these assumptions, I want that f of x0 is related in B, which is okay because I have these assumptions, to coe arrow pi f applied to x1, right? And we can now unfold the definition of coerce. So we get this thing here, coe b alpha of f of coe a. So this is this direction, and this is the other direction of x1. Okay. So that's what we want to prove, or what we want to construct the term. So how do I do this? So first of all, I have x0 and x1 here. And x bar proves that they are equal. And on the other side, I have x1 and coe a this way of x1, which is proved equal by coherence A this way of x1. But I also have a reflexivity of x1. So I'm getting something of this form. Okay, it's the other way around, but I have some rotation somewhere under my table, so on my sleeve, which I'm going to apply. So I'm constructing this term and this filler here. Okay. I have to watch that I'm not doing anything wrong. Okay. So now, if I use this filler and rotate it, so here I need a rotation, I know that f of x0 is equal to f of x1, no, f of coe A of x1, and this is just f respecting equality applied to R. If I really go into details, there's actually a point where I need this the filler as well. I mean the inside, not just this line. Okay, and okay, so is this one? Yes, and by applying now coherence of B in this context, I get that this is the same as what I want. And then I just apply equality. And this filler here is what I need. That is my cohe pi f applied to x0, x1, and x bar. But then I abstract it, and I have finished my construction. So here I also need a filler. So situation for the pi type is that to construct my fillers, I have to go one dimension higher, and this is already very clearly explained in this paper on cubical sets. I'm just shifting it here into my syntactic framework. So whereas if you do the same for sigma, you just stay at the same dimension. So if you want to prove the filler for the first dimension, you only need the assumptions in the first dimension. But the pi type is more interesting in the sense that we really need to go one dimension up. Okay. So, yeah, whereas here in this, I mean, for the coerce, I already needed the coherence. And now when I prove the coherence for the pi type, namely that the function is equivalent to its coercion, so this is a one-dimensional filler, I need the two-dimensional Kahn condition. So I always have to go one dimension up. So at this point, it looked like we need to do fillers for all dimensions, but maybe we don't. So okay, so I want to construct this filler here, which is the filler in the next dimension. So here this is an element of A 0, 0. It's an element of A 1, 0. So if I write this is a composition of these phase maps, right? Here we are in A 0, 1, and here we are in A 1, 1. So now, so what we really want to show is if these two are related and these all are related, then the things on the top are related. And moreover, that the proof for this relation is in some sense equal to the proof in which we coerce. And I'm just going to give the line here on the top without filling the square, which you can do, but I think I would run out of time if I do this. So in this situation, let's consider the following. Tilde A is a function from A0 till A1 to U. And I've constructed this function recursively. But since it's a function, it also, the question is, what is tilde A tilde? Then any function automatically preserves my equality, right? So that means if I have two elements which are the 0 and the 1 projection of my first argument, so I have in A, let's call it 0, 0, in A 0, 0, yeah, which I just write for brevity. This is composition of these phase maps. And I have an A 0, 1, which is an A 0, 1. And I know that they are related, namely that A 0, 0 is related in A 0 to A 0, 1. So I have two elements in the first argument, and now two in the second. I have A 1, 0, which is in A 1, 0, and A 1, 1, which is in A 1, 1. And they are related, namely A 1, 0 is related in A 1 to A 1, 1. Then I know that the first two elements, and we apply the function to them, so A 0, 0 are A 1, 0, no, sorry, tilde A, and now 0. So I apply 0 now to my function. So please view the difference. This is A 0, this is A 1, and this is this relation. Yeah? And you take my relation and move it along 0. That A 0, 0 related to A 1, 0 is in U the same as, and now the second elements, A 0, 1 related A projection 1 to A 1, 1. Right? Sorry it took so long. It's just the logical relation property. If I have two related arguments, then applying the function is related. So the two projections of the function produce related results. So here is all the heterogeneous equality gone a bit mad, right? But the nice thing is, so what do I get? I get a function from left to right here, right? Which is my coerce, right? And what do I need here? I'm exactly in the situation that this is my first argument, this is my second argument, and this is the left-hand side of my equality. And what I want to prove is that this relation holds. Yeah? So what I'm doing here, I'm constructing the second-dimensional Kahn filler from my one-dimensional coerce in this situation. Right? So the nice payoff is that I don't have to do the fillers for sort of parametric bidimensions, which is a bit of an unpleasant thing to do. And indeed, I can apply this to this construction of the pi type and can derive these fillers here directly. Yeah. Okay. So now I have all these beautiful Kahn fillers, and we are happy, yeah? Are we? That's not really what we wanted. What I wanted, what I promised to before, was to construct the path induction, the J, right? So now, to convince you, I have to show you how we can construct the path induction from these Kahn fillers, okay? So the first thing I'm going to do is to construct. Actually, the first thing I'm going to do is I'm going to do over here, I'm going to write down my goal, okay? Maybe it's a bit late. It's 20 minutes left, and now I'm telling you what the goal is, okay? So the goal is to derive J. Yeah, let's simplify things a bit. Let's see A is an element of A. And now I want to have J, and since I'm in France, obviously, sorry, pair, I'm going to use Pauline Christine's version of the eliminator. Yeah? So it's this one for all. So I'm fixing one element, and I'm saying for all predicates which given another element, and the proof that A is equal to B to you, then if I have C of A refill, then for all B in A, and P in A equal B, I have C, B, P, and moreover, the equality J, C, M, A, refill is definitionally equal to M of A, right? Yeah. No, M. Oh, it's just M. No A. Yeah, so this is the definitional equality I want. So, yeah, of A. Yeah. Mm-hmm. And there is a non-dependent version. So if the C doesn't depend on this proof, which is called transport, okay, let's call it transport. I called it subst, but that's just, which is if I have a C, A arrow U, right? And I know C of A, then for all B in A, if A is equal B, I get an element of CB, right? So this is just the special case. And I'm going to do this first, and then from transport via another condition, I can derive J. How does this work again? Okay. So how do we get transport? Now, it's not surprising. I sort of said this already, right? Transport comes from coerce. Oh, I could get confused here. Okay. If we have C, A arrow U, then I also have, what do I have? Okay. C tilde, which lives in gamma equal, but I don't want to live in gamma equal, I don't like gamma equal, so I apply R, which has the type, which type has it? C is equal, equality is as defined before, in A arrow U to C. So this is tilde substituted reflexivity. Okay? And this is the same as pi A B in A, C of A is related in U to C of B. Okay. And now all I have to... Sorry?
You need the equality between A and B.
Oh, yeah. Okay. A, that's, okay, maybe I should call them A0 and A1. A0, A1 in A, and A bar A0 equal to A1. Okay? So now it's clear how I can define transport, because all I need is here the coerce, the first component from U. Now we had a little calculation which I... why am I confused now? Okay. So I wanted to show that this that the definitional inequality holds. So if I apply C tilde R to A0 refill, then I get the refill for the universe. So of C of A0, and the refill of the universe is defined to be the identity. I haven't done this, so I get actually the strict equality, so the computational equality for transport. Okay, so we have transport. So what else do we need to get J? Now, if you compare transport to J, you see that if I change this a bit, I mean, this is a function with two arguments. I can also turn it into sigma, a function with one argument, right? And then what I need to know is, if I would know that this and this, no, that these two pairs are equal, then just by using transport, I can derive J. Do you see this here? So what I need to show is what's also called, it's part of the proof contractibility of singletons in the book, which actually in this case is we only need the fact that singletons are propositional. Namely, I have a proof P that A is equal in A to B, and now what I want to show is that, so given A and B in A, so what I want to show is that A refill is equal in sigma A colon A B, A equals B, to B comma P. And I haven't given the definition for equality for sigma, but it's quite easy. So what I really need is, so I need a proof that A is equal to B, and then up to this proof, Raffle has to be equal to P. And here's a little sort of, if you're very greedy, you do it the wrong way. Let me show this. So on the bottom here, I have my proof A is equal to A by Raffle. And yes, and here on top, I'm confused now. Okay, and here on the top I have the proof P that A is equal to B. This is P, right? And here I also have Raffle is the same. And the question is, so the greedy thing to do is to say, what do I use to prove the equality of the first component here? And you think the obvious choice is P. So we plug in P, and now we have to show that this square commutes, or can be filled. And this corresponds to a particular condition on cubical sets that they're called connected. And now you have to go and prove that everything you do is connected. But you can avoid this by being not so greedy. Who said that this has to be P? It's just lying around, but it makes it makes it difficult, because now we have an open cube, and I can always rotate it. So it's one of the cubes I can fill. So I fill this with the second coerce, and I get the filler for free that this cube commutes. Yeah? So the trick here is not to be greedy, not to use the P which lies around in the context, but instead construct this open square and then fill it. Okay, I think I'm done too early. What have I done? Let me summarize. I have constructed these Kahn fillers. I've defined a new equality for the universe, and then used the Kahn fillers to reconstruct the path induction for equality. So equality type is now the derived equality, the heterogeneous equality applied to reflexivity. Okay, that's it.
Could you detect how you use coherence and conditions equation? Is that right?
Sorry?
Could you detect how you use coherence?
Yeah, the coherence is the thing, the filler that I actually get this equality. Yes, so I ignored some details. Yeah, so I need all the time. I need always the filler as well. To keep things simple, I just construct the coerce and sort of ignore the coherence conditions.
And also how the coherence is.
Sorry?
How does coherence, what sound combination do you use?
No, they show that these two are equal. This is basically the equality proof you need to show that the whole thing is equal. Yeah, that's the filler, I think. If I say something wrong, you tell me. Yeah. Okay.
You could also use P if instead you show that was contractible with the type sigma B equals A. And then, and otherwise you can also use P. You could also prove that that type is contractible by not showing that Raffle is equal to P, but P is equal to Raffle.
Yeah.
And then it seems to like switch in the arguments, and then you try to prove them equal.
I mean, I try. I mean, there's lots of ways to prove this, but I wanted just to use what I have already, and I have just these Kahn fillers, and this way I can just use the Kahn filler without having to do any other reasoning. Yeah.
So the equality between A and B is the squares, and the equality between Raffle and P up to the Coerce equality is the filler in the vertical direction. Yeah. In this filler, in this direction. So you can rotate the filler.
Yeah, but you said being greedy doesn't work because you get on the left side, you cannot use P there. But you could use it if you were proving that what's contractible as the type sigma B equals A,
yeah.
B equals A.
Yeah, but that's exactly what I want just to do, and I want to do it with the ingredients I have constructed. Okay.
Okay.
Yeah. Good.
You have shown how to deal with the reflexivities. What about the symmetries and transitivity?
Okay, so I'm not explicitly dealing with either of them, but I mean I can prove them using J, right? Once I have J, I get all my symmetries, and I mean reflexivities I have constructed previously, right? This was this Raffle, and now I have constructed J. I mean already transport. Once I have transport, that is enough to prove symmetry and transitivity, right?
It depends on what laws we want to be satisfied by their symmetries and transitivities. If we want definitional laws there, I don't think you can define them using the J over.
I mean, the laws are asymmetric. I mean, so there's the law, so Raffle trans Raffle P is definitionally equal to P, but not the other way around. But I get this you get from transport. I mean, what I didn't mention is, and I think I messed it up a bit. I wanted to prove this, but the transport of Raffle is the identity, right? And if you have this, then transitivity, so symmetry applied to reflexivity is reflexivity, and transitivity, where the first argument is reflexivity, is the identity function.
So you get the definitional.
Yeah.
I can just say that that's not how I have dealt with symmetry and transitivity. I have dealt with them directly. Two different approaches.
So assuming that all this what we're doing is modeled in the cubical model, so can one say that, I mean, so on the model level you have to be able to fill boxes, but the corresponding internal statement just is that you have the path lifting property, which intuitively sounds correct, because if you do it internally, you can do it relative to an arbitrary context, and an open box is nothing else. I mean, then, how should I say, such a line segment taking a product with some element of society.
Yeah, no, I don't know. I mean, this is certainly a difference between the model construction and this syntactic approach. This particular trick to derive the higher Kant fillers from the basic one, and I'm still a bit puzzled about this.
I thought that your condition, which all doesn't consider arbitrary boxes, is so to speak the internal language analog of the Kant condition. So if you would critical your requirement, then this amounts to the requirement that open boxes can be filled.
Yeah, I mean, what's happening is this tilde here, I'm actually constructing. So this tilde is a term in my language, yeah, which I've previously constructed. And I know that all terms in my language preserve equality, so I can recur on this. And this is something I have to, when I do the model construction, I have to put it in. Yeah? But here, I know I have done this, hence I can use this, and hence I get my second Kahn filler. Right?
Yeah, but it was also in the model that equality is preserved, as long as you're working with Kahn complexes.
Yeah, no, but I don't know. Maybe. I mean, this is here. It uses this internalization that this tilde is not something which is part of the structure, but it's something I have constructed, and hence I know something about it. But I'm not sure.
Yeah, because you're following the essentially doing induction over the type, structure of types, whereas in the model, of course, it's not inductively presented. So there you have additional structure.
Yeah. I mean, maybe there's a way to exploit this also in the model. I don't know. So.
Yeah, but still, I mean, can you make it a bit more precise? I mean, it's a syntax for the Cubical model, so I'm not insisting on any details.
Okay, so one observation is that underlying the base category for the cuboidal model corresponds exactly to these to the morphisms we have defined here by composition, right? We have 0 and 1, and we can compose them. So we have these phase maps, right? So you have this tower gamma equal 2 and so on, and down are the phase maps, right? And I'm not drawing everyone because here at gamma equal 2 we have also the symmetry, and we can construct maps from gamma equal 2 by going along the symmetry and then going down. Yeah. So in this way we get exactly the underlying the indexing category for the cubical set model.
So in a sense, I mean, it was some time ago observed that every type carries the structure of the group void internal to type theory. You want to observe that in your extended type theory, every type carries the structure of a cubical set in a sense. You see what I mean?
Mm-hmm.
It looks like that. I mean, that's how I understood your reply. I mean,
a type itself is fibered over context gamma, yeah. So here I'm talking about the objects, but then you have to talk about the vibrations. So a type has a bit more structure. The context, yeah, has the structure of a cubical set. That's
well, types and contexts is only a minor difference. I think all notions of models I know, types and contexts are just interpreted objects of some category of model within. There's no qualitative distinction. Well, it depends.
It's more natural with the context.
Yeah, when they are dependent.
Yeah, dependent types. What I mean, yeah. I mean, in context, a type is in a context.
I'm speaking, so to speak, of a type, not in context.
A closed type. Okay, that's the same. Yeah. Then you can do this A equal, which I have done. Yeah. Okay, that's the same. Mm-hmm.
Okay, so let's thank Thorsten.